Hello, my name is and I am a rising junior at. My project is on the simulations of respiratory droplet spray with regards to COVID-19. I am part of the Fluid Dynamics Lab in the Aerospace and Mechanical Engineering Department at USC. My principal investigator is Professor Mittal Luhar, and my mentors are Andrew Chabaran and Shilpa Vijay, both of whom are PhD candidates. As we face the coronavirus pandemic, new restrictions such as face masks, social distancing of 6 feet or 2 meters, and stay-at-home orders have been enforced to minimize the spread of the virus. There are many journal articles describing the characteristics of virus droplets and how effective masks are. Many of these journals use Schlieren imaging, as pictured here, to capture the droplet flow. However, I wanted to look at the computational side of this topic and examine the results fluid dynamics software could produce. For this project, I will be looking at the dispersion pattern of droplets released through breathing, talking, coughing, and sneezing, determine whether 2 meters is an adequate distance or whether it should be more or less, and looking at how effective masks are and by what percentage do masks reduce the particle velocity in cloud. For my project, I use ANSYS Fluent, a computational fluid dynamics software, to create my simulations. I created an axisymmetric domain of 2 meters by 0.5 meters to reflect on the recommended social distance. I used the domain to create 4 grids, each with an increasing number of cells, therefore also decreasing the cell size. Creating different grids would ensure my results produced were not dependent on my grid, which would allow me to reach mesh-independent solutions. I also ran experimental data from journal papers as one last step to verify my geometry and mesh. Once my grids were created, I set boundary conditions specific to each type of exhalation method and ran simulations for each of the 4 cases. Each of the 4 cases was run twice, one for someone not wearing a mask and one for someone wearing a mask. These plots demonstrate the jet spreading of particles. Figure 4 shows the jet spreading has grid independence, meaning the results do not depend on the mesh I created. I tested several grids ranging from 11,000 cells to 99,000 cells, and all produced similar results. I also compared my plots to published journals such as Hussein's velocity measurement paper. Hussein's data is represented by the black line on my plots. Figure 5 represents the self-similarity of the jet. At any distance, the jet will be similar to a jet at a farther distance. I chose to show the jet spreading at 0.125 meters, 0.25 meters, and 0.375 meters. The jets all have the same pattern, which demonstrates their similarity. So these are my simulation results for the talking, coughing, and sneezing cases. The x-axis represents the distance in the axial direction, and the y-axis represents the distance in the radial direction. The colors in the plus describe the velocity at a certain distance. Red is a high velocity and blue is a low velocity. From my experiment, I concluded that in the no-mask plots, the velocity decreases gradually, as demonstrated by the wide range to reduce the velocity. In the mask cases, there is a sudden change in the velocity. This sudden decrease in velocity causes air resistance, also known as drag, to become very significant and minimize the distance the particle travels. From my plots, I also noted that wearing a mask reduces the velocity of particles exhaled by 75 to 80%, depending on the type of exhalation method. Lastly, 2 meters is an adequate distance for social distancing, since there is a significant velocity reduction in transport of droplets. If I were to continue this research, I would take into more factors into my simulations, such as temperature, humidity, and situation conditions to see how this would affect the droplet velocity and distance. I would like to thank my PI, my mentors and lab partner, and the SHINE team for a memorable experience.